Yeah, welcome to my talk about digital twins in machine vision applications. My name is Sven Wanner and I'm from Artificial Pixels. In my talk I will give a short introduction into, or a quick definition of what I mean with a digital twin in machine vision applications. I will go over some typical use cases or application areas. Will show you a little bit about the value a digital twin can bring to your project. And in the second part of the presentation, I will talk about maybe one of the most famous topics related to digital twins, the generation of synthetic data. The Digital Twin Consortium defines a digital twin is a virtual representation of real-world entities and processes synchronized at a specified frequency and fidelity. This is a very broad definition, which is normally good for a definition. For the sake of this talk and digital twins in machine vision, I want to make this a bit more concrete and say a digital twin is a simulation of sensors, objects, and processes applied to these sensors and objects. This means digital twins are, in our view, not just 3D models, but the entirety of relevant data streams produced by your vision application. Typical application areas of digital twins are system design and risk minimization. If you start your project really from the beginning with the digital twin, it brings you a lot of benefits for both the hardware development and the software development. For example, your hardware team can start right from the beginning to evaluate their hardware planning. Would it be better to have the cameras here or there? Would it be better to have the lighting here or there? So it really helps to virtually optimize the hardware system, and thus you can achieve some optimizations before the hardware was built the first time. And also your software team can early start development and parallelize this with the hardware team, which normally shortens your project timeline quite drastically and, as said, minimizes risks of failures. A second application area we call on-demand simulation. What we mean with that is that we more or less see the vision application as a computer game. So the simulation then is built in a way that you can integrate it in your software solution and trigger it live with your software and get the data back as you would work with the real-world system. And this has, of course, a lot of benefits in some applications, but also for your development team. Each developer can have its own vision system ready to use anytime to experiment or whatever. And as said, one of the most famous application areas is synthetic data creation. In this mode, we normally use the digital twin not in a live interaction mode, but use it as a data generation machine. So the purpose then is to vary all the free parameters of the system in a way that you can, in a smart way, create big data sets to train models, for example. And with this synthetic data created, you can, of course, start pre-training a model. You can extend your real-world data sets or handle edge cases. And synthetic data are also quite nice to analyze your real-world data sets or gain deeper insights into your overall problem. And to summarize this, the benefits a digital twin can bring to your project starts really in the beginning of the project. You can early kick off your project. You can start your software development early. You can optimize your system quite well virtually and with really low costs and in short times. You can use it as a live interaction tool. You can create big amount of data at scale. And one of the most overseen benefit of a digital twin is when it comes to changes. When your customer starts and suddenly says, okay, I want to use this box instead of that, or there's another camera type, maybe cheaper and better, could we use also this camera type in our project? Then using a digital twin or simulation, you can quite easily and very fast adapt to such changes. And as a cherry on top, digital twins also can produce a lot of nice advertisement material or info material for your customers. Let's now come to the synthetic data topic. I quite often use this image to demonstrate one thing, because often I meet people that are either skeptics or enthusiasts when it comes to synthetic data. The skeptics say, oh, synthetic data, this will never work, it's too unrealistic, will never work in real-world problems. And the enthusiast says, oh, cool, we can do everything with it. And as always, the truth lies somewhere in between. And yeah, in a couple of slides I will show you how synthetic data actually can look like, not like this. But first I want to quickly talk about how we can make synthetic data that actually works. And for that I prepared a couple of slides to explain an idea. So here we see just a stupid, it's very simplified data set, 2 dimensions, 2 features. It's already annotated. Let's say blue is not okay, yellow is okay, or the other way around, doesn't matter. The thing I want to tell you with this plot is real data normally have a certain distribution in the feature space. And if we would train an AI model on such a data set, it would try to find a function in this feature space to separate these distributions optimally from each other. And that's what a model normally is doing. And now let's add some bad synthetic data. We added some synthetic data in these small red circles below. And why are they bad? They are bad because of 2 reasons. First of all, you immediately see they don't have a normal distribution. They are really in a really tiny area in the feature space, which normally means they are kind of too perfect. There's not enough variation in the data. And the second type of problem is they are quite off from the distribution centers. So both of these problems are very common with synthetic data. And if we now apply the model we trained before, oops, our synthetic data works quite well in this example. So does this mean our synthetic data are good? Of course not. If we would train the model just on the synthetic data, then this could be a possible solution, and you immediately see it wouldn't work in real life. And this is the main issue that happens with synthetic data if you don't do it correct. But there's another problem. In the red ellipse, I added some new real-world data points that we don't have in reality because these are these typical hard-to-capture cases. They are really hard to capture, really rare occurring events. And in reality, we don't have this data, but your distribution would look like that if you would be able to capture all of the data you need. And if we apply our model that we trained on the data, we immediately see this is where data models fail on these hard edge cases if we don't have them in our data set. And then this is the image what I want to show you how good synthetic data should look like. So we see we have two very important parameters. We have these normal looking like distribution of the data. We have the same distribution centers, means the images are really similar to each other. And if these 2 parameters are valid, then we have a very, very big chance if we generate edge cases with such a digital twin that we really reproduce what we would measure in reality. But another point is how can we use synthetic data to really benefit our model when we use them? And for that, I want to illustrate it with these 4 pictures. Question to you is, are you able to extract any information of these 4 images? And I promise there is an information hidden in these 4 images. I will not wait for answers because I'm quite sure no one can do it. But if we change the representation of the data and maybe arrange them in a 3-dimensional volume and interpret the 3rd new dimension as the time, you will immediately be able to extract the information. As a human, what we are doing, we find the hidden statistics now through the time dimension, because we see the statistics on some pixels is very varying and on others it's static. And an AI model is exactly doing that. It searches for the hidden statistics in huge dimensional spaces. And how can we help a model to learn these hidden statistics better with synthetic data? And for that we end again with this image we have in the beginning of the topic. So now we see how synthetic data can look like. You see now on the left side images captured with a normal digital camera, and on the right side images generated with our synthetic data pipeline. And you see we can perfectly reproduce the real world data, but reproducing the real world data does not make so much sense, you would say. But the only thing I want to show you with this is that we are able to generate data points that are really, really close to the real distribution. And if we can do that, then we can in the next step start changing things. So if we now start in the digital twin, change the illumination, we change the geometry, we can say we change the color of the objects. If we start changing the things the model should learn that they are not important, then change it. Change it as much as you can, and this will help the model to learn what is not important for me. You can also, of course, add defects and imperfections, and all of these possibilities you have having a high-quality digital twin that is able to produce such synthetic data. But changing colors and everything I showed you before, I hope you can see it. Maybe it's not optimal here, but all of these changes are happening in the image domain on the model. But there's another domain where variation happens, and this is on the physical level. Optics generate defects, generate changes. Sensors generate sensor noise, very specific normally to the sensor you use. And we also simulate that, and you see on the left side, or if you would be able to see it, you would see this is a crop from the real image, and you see the sensor noise, you see the optical defects. The middle image is a pure rendering, and it's too perfect. You see crisp, sharp edges, you see no sensor noise, and after our simulation pipeline on the right, you see that we can get really, really close to the real-world distribution. And this is how we can really help an AI model to learn what it is missing on not complete real-world data sets. So I think I was quite fast now. Yeah, 1 minute faster. So I'm open to your questions.